Settle in. This is Unintended Consequences, Episode 7 for May 12th, 2026. Today's story is one of those rare examples where the cure was almost worse than the disease, at least at first. In the spring of 1928, a young engineer named Thomas Midgley Jr. stood in a laboratory in Dayton, Ohio. He demonstrated that a new synthetic gas could be breathed without harm and would not catch fire even when a lit match was held to it. The compound dichlorodifluoromethane soon became known as Freon 12. Within a few decades, it and its chemical cousins had replaced ammonia and sulfur dioxide in millions of refrigerators and air conditioners. They made safe mechanical cooling available to homes, offices, and cars around the world. Yet the same stability that made these chlorofluorocarbons so useful allowed them to drift intact into the stratosphere. There, they began steadily dismantling the ozone molecules that shield Earth from ultraviolet radiation. Midgley worked for General Motors' Frigidaire division at a moment when household refrigeration was expanding rapidly but remained dangerous. Leaking ammonia or sulfur dioxide systems had already caused deaths and injuries in homes and restaurants. The industry needed a refrigerant that was neither toxic nor flammable. Midgley and his team screened hundreds of compounds before settling on the new class of chlorofluorocarbons. Their carbon-chlorine-fluorine bonds proved remarkably inert under ordinary conditions. The first commercial units using Freon 12 reached the market in 1930. By the late 1930s, DuPont had licensed the technology and begun large-scale production. At the time, atmospheric chemists knew little about how trace gases behaved once they left the troposphere. The stratosphere was still regarded mainly as a stable reservoir of oxygen and nitrogen. Midgley's solution, therefore, appeared to be an unqualified public health advance. It removed one of the last technical barriers to widespread mechanical cooling. Production of CFCs grew steadily through the 1940s and then accelerated after World War II. By 1950, more than 100,000 metric tons were manufactured annually. These were chiefly for domestic refrigerators and the new window air conditioners that were transforming American summers. In the 1960s, the same compounds found new uses as propellants in aerosol cans and as solvents in the electronics industry. Industry literature of the period described CFCs as ideal because they performed reliably across wide temperature ranges and required no special handling precautions. A handful of researchers had begun to measure their rising atmospheric concentrations. Yet these measurements were treated as curiosities rather than warnings. No regulatory body saw reason to restrict a substance that had never been linked to any observable harm on the ground. The first clear indication that something was amiss came in 1974. Chemists Mario Molina and F. Sherwood Rowland at the University of California, Irvine, published calculations showing that CFC molecules could survive long enough to reach the stratosphere. Their ultraviolet light would split off chlorine atoms capable of catalytically destroying ozone. Their paper in Nature received modest attention at first. The chemistry was still theoretical, and ozone levels had not yet shown dramatic change. 5 years later, however, ground-based measurements from the British Antarctic Survey Station at Halley Bay revealed that October ozone columns above Antarctica had declined by roughly 40% since the late 1970s. Subsequent aircraft and satellite campaigns confirmed that the depletion was concentrated in a seasonal hole. Its size reached more than 20 million square kilometers by 1987. The causal chain was straightforward once the mechanism was understood. The very chemical inertness that had made CFCs safe in the lower atmosphere allowed them to accumulate and then release reactive chlorine at altitudes where ozone is most effective at absorbing ultraviolet light. Second-order effects followed quickly. Increased surface ultraviolet radiation raised estimates of additional skin cancer cases in mid-latitude populations. The seasonal Antarctic hole altered expectations about how quickly the atmosphere might recover even after emissions stopped. A third-order consequence emerged when governments and companies began searching for substitutes. The first generation of replacements, hydrochlorofluorocarbons, still contained chlorine and therefore required a second round of controls. The scientific consensus solidified rapidly after the 1985 discovery. In September 1987, diplomats meeting in Montreal produced the first binding international agreement to phase out ozone-depleting substances. Developed countries committed to a 50% reduction in CFC production by 1998. Subsequent amendments accelerated the schedule. Production of the main CFCs ended in industrialized nations by 1996. The Montreal Protocol is widely credited with preventing far larger ozone losses. Satellite records now show that the Antarctic ozone hole has begun a slow, uneven recovery. Full restoration to 1980 levels is not expected until roughly 2070. The transition to substitutes was not without its own complications. Hydrofluorocarbons, adopted in the 1990s, proved to be potent greenhouse gases. This prompted the 2016 Kigali Amendment to address their climate impact. Yet the original decision makers in the 1930s could not have anticipated either the atmospheric chemistry or the institutional machinery that eventually addressed it. One clear principle is that chemical stability, while desirable for safety and performance on the ground, can become a liability once a substance enters a region where different reaction pathways dominate. A second is that global commons problems often require monitoring systems capable of detecting slow, cumulative changes long before local effects become obvious. Finally, the Montreal experience suggests that international agreements can succeed when the underlying science is clear, the number of major producers is small, and technically feasible substitutes exist. The forward-looking question this story leaves us with is how many other widely used compounds we are releasing today whose atmospheric lifetimes and reaction products we still understand only incompletely. That wraps today's case. The lessons travel further when you share them. Send this episode to someone who'd find it useful. We'll see you tomorrow. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.